Awesome. Thanks, Dave. And thanks to the organizers for inviting me to speak. And of course, the folks at IPAM for putting all this together and hosting this workshop, if virtually, which is still, so far, it's been very nice. I'll say this, I have, another monitor over here. I'm kind of watching the chat, sort of. I think I've gotten good at it. If I do miss something, of course, Dave, please feel free to interrupt me with questions. I appreciate the questions, interruptions, the lively chat. I was actually giving I don't know if you could call it giving a talk, but I was a guest speaker at my son's classroom. He's in the 3rd grade in December, and I was maybe about as nervous for that one as I am for this one, because it can be pretty quiet. It is, deafeningly quiet right now, but I was afraid because with kids, but I can report, lots of you have kids, I guess, in school, but for those that don't, I can report that the usual kind of juvenile humor is alive and well if restricted to the chat. So I'm happy for interruptions, the odd toilet humor joke, whatever. In any case, I'm continuing with, as Dave said, with this abstract approach. I'll be more focused, I think, still at a very high level, but I'm going to be talking about, I guess, basically just one theorem, or 2 theorems, I suppose, but I'm going to be talking about the classification theorem and kind of how we get there and the ingredients involved. But as I said, in a very high level. So I don't know that I'll throw quite as much information at you. A lot of the stuff, I'm not going to be encyclopedic. A lot of the stuff that I'm going to talk about is certainly due to other people. Most of the stuff probably is due to other people, but few things I was involved in were with my wonderful co-authors. So joint with Jamie Gabe, Chris Schaffhauser, Aaron Tequisis, and Stuart White. Hopefully the handwriting will be legible enough, or not small enough. My students haven't complained, but they never do. Right. So I'll restate the main classification theorem. For C-star algebras. So here, A and B are unital, separable, simple, and nuclear. They're also Z-stable and in the UCT class. And the statement that Kristen gave is basically what I'm going to say now. So you can tell these C-star algebras apart using K-theory and traces. Okay, so I'm going to write this. We've taken to writing this K-theory and traces. This invariant is KT with a subscript U for unital. So if they share the same invariant, K-theory and traces. So here, I have to move your faces slightly to change colors. KTU, what do we mean by this? I want to be at least somewhat specific. So we're talking about the K0, K1 groups, the class of the unit in K0, the tracial state space, and there's a pairing or connecting map that keeps track of the interaction. I guess I can write it out. You're going to have to move your faces. Actually, move you to the other screen. So this keeps track of the interaction, as I said, between K0 and the tracial state space. So if you like, it's a pairing. Take a trace and a K0 element gives you a real number. So if you have a trace and the class of some projection, this gets mapped to just evaluate the trace at the projection. And we've taken to using this notation, and this isn't a genuinely new invariant. The reason we're writing this is to make the distinction that in this new approach, this abstract approach, we don't make much use of, or any use really, of the order structure in K0. So as opposed to usual LE invariant, where you include the order structure, here we don't. So that's why I'm using KTU, not because it's some new thing that we defined. Kirsten, I think, went over the hypotheses relatively well, or very well, sorry. But I guess I wanted to include a few more things about Z and the UCT. I really consider this kind of a single hypothesis. I won't say very much about that in this context. I do want to say, like I said, a few things about Z and the UCT. So let me say, not very much. So more often than not, you don't really care what Z is. So, we were talking about this earlier. What is Z? And for the most part, you want to know what Z stability is, as opposed to what Z is. And of course, I mean, at the end, you really need to know, but it's enough to get a working knowledge of what this means. And I can at least define or give you an idea what this is briefly here. So you absorb Z, the Jiangsu algebra, tensorially, if and only if, so here A can be in the theorem. I think you only need like separable and unital. If and only if there exists a unital star Hom from one of these dimension drop type algebras into the central sequence algebra of A. So what is this? Let me say what these things mean. So here A, well, actually I like purple. A sub infinity here, we just mean the what we're calling the sequence algebra of A. So you take L infinity of A, so sequences that are bounded in norm, modulo those sequences that tend to zero in norm, so C0 of A. Of course, A sits in here as constant sequences, so you can look at the things in there that commute with A. That's what I'm writing here. And Z23 was defined earlier, and this thing is a subalgebra of continuous functions on the unit interval with values in 6x6 matrices, okay, with scalar entries, where at one end, these things look like 2x2 matrices. So function in here evaluated at 0 returns basically a 2x2 matrix, so M2 tensor 1. And at the other end, it's in, I guess I should write 1 tensor M3. Okay. This is due to, I guess, ultimately, Mikhail Rodham and Wilhelm Winter. This kind of description, I think, also building on works of Thoms and Winter. But there's one way of describing Z stability, okay? And as Kristen mentioned, so it's a fact, another bullet, that if A is as above, a unital C-star algebra, then KTU of A is isomorphic to KTU of A tensor Z. Okay, and if you're talking about C-star algebras and is in our theorem, A tensor Z is also a C-star algebra as in our theorem. So this is, already more than 20 years ago was predicted that this is necessary. A has to be Z stable to be classifiable. So, and maybe I'll say a few things about the UCT very briefly. I mean, I meant to give kind of a high-level introduction to, this approach, which has a ton of ingredients in it, and a lot of them very technical. One of them, of course, is KK theory and the UCT, which deserve another week's worth of many courses just introduced. So here, I'm not going to do it justice, and actually, I'm just going to give you like a consequence, I guess. Okay. And this is one of the ways that it gets used, and I think it's nice to at least be aware of it, because it shouldn't be, I mean, it is kind of a black box, but it shouldn't be that mysterious, at least from a high level, kind of philosophical point of view. So you have, let me write this. So you have homomorphisms. Imagine you're thinking about this theorem, right? You have maps at the level of K0, so maybe you have some homomorphisms. Here you have some homomorphisms. Here, the level of K1, and you want to get a star homomorphism out of it. And I mean, lacking some kind of real rigid internal structure, which is how a lot of this was done when you were talking about inductive limits, for instance, AF algebras, you don't really know where to start. One place where you can start is by lifting this to a generalized star homomorphism. So that's how you can think of KK, so generalized star homs from A to B. And what the UCT says is that you have a surjection, a very nice one, given by the Kasparov product. Well, that's not what the UCT says, but the UCT implies that you have a surjection like this, okay? And, the UCT is some exact sequence related to this, describes the kernel and whatnot. Okay, but this is at least giving you some flavor of how the UCT can be employed, okay? Oh, there's some talk in the chat about the order and the invariant. Right, so I guess this is something that we can certainly get into after the talk, but we don't use the order at all. And it's not that the order is, how to put it, I mean, if we don't use it, I guess it is in a sense irrelevant in our approach, but it's that the information that the order gives you for the class of C-star algebras we're considering is already contained elsewhere. So it's not that it was unreasonable to consider it in the past or anything of the sort. No. And I guess Chris is saying it more carefully than I am. There you go. Okay. So generalized star homomorphisms is a bit of a cop-out, and there was some discussion in the chat. So I opted to maybe, how am I doing on time? I started 12 minutes ago. So I opted to maybe cut something out later. We'll see how I do with time, to at least say a word about what KK is. And really it's just a word. So, I'm kind of improvising. So the idea, look, I mean, there's part of the power of KK, there was some description given in this breakout room, is that it has lots of different interpretations. The one that we use the most predominantly, you can think of it as some sort of like formal differences of star homomorphisms. Okay, with an equivalence relation, modded out by an equivalence relation based on a kind of loose notion of homotopy. Okay, this is the Kuntz picture of KK theory. And, if you like elements in, just to make it a little bit easier to kind of parse, from A to C, a generalized star homomorphism, you think of like a pair, okay, where these are star homs not from A to C, because, in general, even from A to B, even if B is a bigger C-star algebra than C, right, there might not be any. So you actually look at representations, if you like, so from A to B of H. Okay, and the difference of these two things is compact. Okay. So this is what I mean by a kind of formal difference. A star homomorphism gives you a formal difference. In a sense, you can take, if you have just star homomorphism from A to C, you can certainly turn that into something like a phi comma 0 if you just tensor phi with like a rank 1 projection. And if you want to do this in general, then it gives, I mean, this is very involved, but if you want to do this in general, here you would consider, multiplier algebras of, stabilizations and whatnot, because you need a lot of room. Okay, but this at least gives you a feel for it. Okay, but as I said, I mean, part of the power here is that it has lots of different interpretations. One of these interpretations, for instance, is that you can get KK elements from extensions of C-star algebras. So this is something that we'll actually be using. All right, enough of that. Our approach, and this is a new approach to let me undo that, classifying algebras, is by classifying star homomorphisms. Okay, so this is really the content of the approach, and I mean, it's an old one, classifying star homomorphisms, so this isn't a new idea. And the scheme, or rather goal, is to produce an invariant of C-star algebras, a functor really. We're writing KTU underline. We're calling this the total invariant, somewhat ominously named, with the following properties. And there's lots of properties. I'll just mention two important ones that we'll focus on. Every suitable morphism at the level of the total invariant, so every KTU underline morphism, is induced, so it comes from a star homomorphism, is induced by a suitable star hom from A to B. Okay. So, if you have one of these, then you get a star homomorphism. This will involve K-theory and traces as well, and I'll describe it in a bit, but, a star homomorphism will naturally induce a map at the KTU level. This is what we refer to as existence, or what is referred to as existence. And second, that, this phi, just to say it, I guess, succinctly, this phi is unique up to, suitable notion of equivalence. And I'll say a lot of what these suitables are. And this one here is what we call uniqueness. Okay. Right. So, if you have two, suitable star homomorphisms that induce the same total invariant or map at the level of total invariant, then they should be equivalent. And equivalence here isn't some mysterious thing. It's what's called approximate unitary equivalence. Okay, so what we mean by this, so phi and say psi are approximately unitarily equivalent if there is a sequence of unitaries. So I haven't said what A and B are, but if you like, for the whole talk, if you want, you can assume that there is in my classification theorem, particular unital, such that if you conjugate one, you get the other in the limit. Okay, so phi of A minus UN star psi of A UN tends to 0. Okay, as m goes to infinity. Okay, so this is what we mean by approximate unitary equivalence. This is the equivalence relation we're talking about here. All right. And there's some other bits that you'll need besides these two. These are the two main ones that you usually want, but well, I might as well write. You'll also need things like this. So it's important. You'll have to relate these two invariants. If you have isomorphism at the level of the, KTU invariant, then you should get isomorphism at the level of the total invariant. And you might think, well, what do we need this thing at all for? And it's of a subtle point. The point here is that the information that you need to classify morphisms is more, in fact, and this has been known for almost 30 years, I guess, thanks to work of Thomson-Nielsen, than what really KTU contains. On the other hand, you can recover the isomorphism class, the total invariant isomorphism class from this KTU in a sense, but you can't reconstruct, whatever information is contained in here in some canonical way from just the information that's in KTU, okay? But anyway, this isn't something that I want to focus on. And second, the identity maps here for everything involved should be suitable, whatever suitable means. Okay, and I bring this up because you can kind of sketch made an argument for how all this works. How do you get from morphisms to algebras? So assuming all of this, so assuming we have this.
Oh, Jose, there's a question in the chat. I want to bring your attention to it.
Oh, it does make a difference. So, getting, characterizing asymptotic unitary equivalence in this way, it's certainly something that people have thought about and we've thought about, but I guess you'd expect it to be more difficult. And there are reasons for this, and I'm sure Chris will write it in the chat. So, in a sense, this is not a closed equivalence relation. So that's one of the, I guess, if you want to put your finger on one of the reasons. But I guess the other thing is that we can do this one. It's a little bit easier, and we don't need to kind of jump through the hoops in order to get asymptotic equivalence, which other approaches do. And I guess I'll outline a little bit of that. I think the answers in the chat are better than the ones that I gave, but good. Actually, the chat works really well for that. So, all right. So assuming we have all of this, how do you classify algebras? You start with your KTU isomorphism. And again, this is a fairly classical kind of thing, what I'm saying, but I thought it's worth going kind of through the motions for people that have never seen any of it. You have an isomorphism at this level, okay? I just said that this gives you an isomorphism. So I'll just write exists, an isomorphism, between the total invariants. So you have two morphisms, their inverses between these two things. Okay, capital phi, capital psi, which implies by existence that you have star homomorphisms, suitable star homomorphisms, not necessarily isomorphisms. Okay, inducing capital phi, inducing capital psi, and in particular, this thing's a functor, so the composition of the things that these things induce is the identity. If you just rewrite this, keeping in mind that this thing's nice functor, then what you end up getting is that the total invariant induced by this composition is the identity. Oh, what I wrote. Well, anyway, okay, IDB, I guess. And similarly, you could do this one as well, okay? So you get both of these things, which by uniqueness tells you that these two compositions are approximately unitarily equivalent to the identity. And I wrote down the wrong identity, which is what, I think Aaron was mentioning in the chat earlier, exactly what you need to use this Elliott intertwining argument. When you have precisely what I've written down here, there's some mild restrictions, but when you have what I've written down here, then A and B are isomorphic. Okay. So you start from here and you go through the classification for maps, and this is what you get. All right. 23 minutes in. Well, okay. I find that if I give this talk and I don't tell you what the total invariant is, it feels a little empty, and people ask about it anyway. So the total invariant, it is important, right? We've seen it used, and without it, this kind of argument gets a lot messier or just undoable without suitable replacements for it. But in truth, I'll say, I guess to kind of motivate the definition, that you shouldn't stress out about it, because most of the arguments involved in existence and uniqueness are really KK theoretic. Okay, they're more based on the KK side of things and related gadgets than they are with what I'm about to write down. Okay, nevertheless, it's important to be able to package it all neatly in terms of this total invariant in order to carry out this kind of argument and other things. So I guess my point is, please don't stress out if you don't know a few of these things. Especially, I think we technically defined K0 in the first talk today, and now I'm about to say, so the total K theory of A is the first thing. So if you just learned what K0 is, then you really shouldn't worry about this at all. So what is this? This is collecting, I'll at least write it. This is collecting all K0 and K1 of this C-star algebra, but with coefficients in Z mod n, whatever that is. Second, so this is, a K theoretic gadget. Second, the tracial state space. Then you have a kind of hybrid algebraic K1 or topological K1 group, the Hausdorff algebraic K1 group of A. What is this thing? As in the definition of K1, you can consider the infinite unitary group of A. Okay, so this is an inductive limit of unitary matrices over A with the usual unital connecting maps. And here you look at the derived or the commutator subgroup of this group. and take its closure, the inductive limit topology. And this turns out to be a normal subgroup. You can mod out by it, okay? And this is what this group is here, okay? And this is, I mean, none of these ingredients is really new, okay? And even their use isn't new in this kind of context. So this group has been looked at from the classification point of view for a long time, maybe 25 years or so. In any case, then the final thing, I guess final things, just the class of the unit and various connecting maps. Connecting maps. Okay, I mean, you saw one of these earlier, right? So I'll just say, e.g., you saw one of these earlier from K0 into the affine continuous functions on this nice convex space traces on A. Really, you just take the class of a projection, and what function does it give you? Just evaluating a given trace on that projection. Okay, that's the way to think about it. But there's also other things to worry about here. So just to give some examples, you have a natural map from K1 alg into K1. Basically, just take the class of your unitary and then just take the class of your unitary. Turns out this is nice enough. But there's other things, there's kind of an inverse to this Delahaye-Scandalis determinant, what we're calling the Thompson map, connecting these two groups as well. And there's lots of other things, so I'm not going to get into this, but there's information that you need to keep track of here, as we have learned kind of the hard way. You can ask us later about what I mean by that, that you really need to keep track of there. Right. I guess I've kind of stepped all over my comments that I was going to make. I really was going to say that these ingredients are not new, and even their use in classification is not new. I mentioned Thompson and Nielsen from the early 90s, but more relevant and more recent is the work of Gonglin and Yu, where you'll find very much related objects and even some of these very same objects in similar contexts. You have this qualifier abstract in our approach, and this is as opposed to other approaches, which are in a sense more concrete, relying on specific internal structure, but you'll still see some of these same tools in use there. Okay, so I guess putting them together in this very specific way, in the way that we use them, is a little bit different, but the general, this has all kind of been in the air. I guess I should state a theorem. So actually, I'm going to cheat here and do something. I don't want to run out of time. I go until 1:30, I think. I got 20 more minutes. Is that right, Dave?
Yes, 20 more minutes and
right.
A little bit.
But in any case, I'm just going to paste. Let me see if this works. Oh, I can't do this on a blackboard, but there you go. So here's a theorem. Call this our classification of embeddings theorem. And it really just says that we can achieve those goals that I mentioned earlier, existence and uniqueness, using our total invariant. Okay, so it's a little redundant in a sense. I've allowed myself to be slightly more general here. So A is unital separable nuclear, okay, not necessarily requiring simplicity, and B, unital separable simple nuclear and Z stable, not requiring UCT necessarily. And I guess suitably interpreted, you don't really need the traces, but then that's also, I think, the point that Kristen made earlier, that this is really then just reduces to work of Kirchberg and Phillips and their classification of purely infinite C-star algebras. Okay, but this, with the traces, is, I'm putting the names up, Gabe Schaffhauser, DeQuistis, and White. Okay, and here I've I guess been a bit more specific. Suitable morphisms. Now that we've seen at least what the total invariant is, well, unital means it preserves this class of the unit in K0. Faithful, I guess you can explain it as follows. This gives you a map at the level of tracial states. Okay. And I guess the way it works is you get a map from, traces on B give you traces on A, right? And you want these traces to be faithful. Okay, it's one way of saying it. And compatible means it plays nice and interacts the way you'd want with all these various connecting maps that I didn't define carefully. Okay, but these are things that unital faithful star homomorphisms would do if you looked at the maps that they induced at this level. Okay, so this is something that you should expect. All right, that's the theorem. As I mentioned, one corollary of this is just a classification of algebras theorem that I stated at the beginning. Another corollary that might be of interest, I'll write this one out here, has to do with automorphisms. So if you look at automorphisms on A, modulo approximately inner ones, or maybe, well, I guess the same. So here, what do I mean by this? One way of thinking about it is just automorphisms alpha that are approximately unitarily equivalent to the identity. Okay, so you want to identify this group, and as it turns out, this is isomorphic to, well, I'll just write out of this thing, whatever that means. So unital automorphisms, unital faithful compatible surjective maps from this thing to itself. And here A, you want to apply this directly. So A should satisfy both the domain and the target hypotheses here. Okay, but you can then get a statement like this from this theorem. And you might have seen me talk about this before, and some of the rest of us. And I mean, this can be generalized some, but it's not really worth, I think, for the purposes of this week. You can weaken some of these conditions to a fair amount, passing these hypotheses onto the morphisms themselves, in a sense. And this is something specialists can ask about this later if you're curious. But if this is the first time you see something like this, then don't stress out. In the last, like 15 or so minutes, I was hoping to run out of time, but I'll mention some of the ingredients. And if I have time, a broad outline of the argument. Actually, I shouldn't say I was hoping to run out of time, not really, because Chris will be also kind of homing in on one of these steps, kind of where the meat really is in his talk, I think. And I want to kind of set it up a little bit. Nothing in the chat. So the first thing is that it turns out it's enough to classify maps, and I'm being vague, maps from A to this sequence algebra. Okay, remember this was L infinity mod C0. Okay, I mean, you need to massage the statement here a bit, but it's enough to classify star homomorphisms, certain star homomorphisms from A to the sequence algebra, which at least philosophically should be easier. B infinity here is bigger, so it should be easier to produce maps. On the other hand, it might be harder to prove uniqueness statements, but we'll see how we can deal with that. And the fundamental tool in dealing with this is the following. So we'll consider the trace kernel extension. Or maybe not tool, I don't know, fundamental framework. Okay, and this has been studied heavily and played a big part in lots of this Tom's winter conjecture that you've heard of, and in classification itself, since like the breakthrough work of Matsui and Sato in 2013, about is when that appeared. All right. So what is this trace kernel extension? Okay, question in the chat that was also answered. All right, so you have your sequence algebra B lower infinity. In there, you're going to look at a certain ideal. This is an ideal of, I'm not going to define it carefully, actually. I was going to, but these are tracially null sequences in B infinity. Okay, and you can define what I mean here properly. Okay, sort of take sequences of traces and sequences of elements, and in the limit they should be suitably small. Okay, and you write B upper infinity here for the quotient. This is the trace kernel extension. This thing is called the trace kernel ideal. Now, each of these three things has their own useful properties. I'll mention some of it. I don't know if it'll generate enough discussion to talk about next week, but we're replacing B with B infinity, and it is a suitable replacement. It's nice enough. It inherits some nice properties from B. This is a big thing, so you have to be careful how you say it, but it's suitably regular. Okay, Z stable, if you interpret it right, and has nice comparison properties. You can tell apart the order for positive elements using traces and whatnot. If you know what this means, it has stable rank 1 and other things. Okay, it's a suitably nice replacement for B, which was very nice. B upper infinity, on the other hand, has a rich von Neumann algebra-like structure, which I think was alluded to actually in Stuart's introductory talk. When he mentioned that, we start essentially with Kahn's theorem, and this is why. Okay, this thing has a rich von Neumann algebra-like structure. You can think here of it, it's not, but you can think of it like a 2-1 factor or 2-1 factor ultra power. Okay, and I'm not going to say a whole lot about the trace kernel ideal. Yes, it's nice enough and big enough in B lower infinity that it helps run the KK machinery. And I guess, in a few minutes, I'll give you kind of very, very broad steps. I hope the talk hasn't been too broad. It's sort of a danger when you're giving a talk like this to say nothing for 50 minutes, or to then say too much and none of it's intelligible. So I don't know where I am, but I'll give kind of a very broad outline. Okay, how you might even get a map at all, right? I mean, that's a question. You have this map at the KT level. How do you produce star homomorphisms at all? Somebody's asking about in the chat about, and I think Chris is about to give a better answer, K1 algebra versus K1. And of course, we mean the Hausdorff version. I guess rather tthan answer your question, Robert, I'll mention that, you don't really need this thing when there's enough projections around. Okay, which is one reason why you didn't see it necessarily popping up all over the place early on. Okay, when there's enough projections around, this doesn't give you any more information than what you already had. I don't know if that helps. All right, broad outline. So you start with your trace kernel ideal. I'll write it here. Oh, what is A? Oh, 0. Okay, so you start again. And remember, we're proving this classification of embeddings theorem. So we start with a map at the level of the total invariant. Which you don't need to remember what it was. Let's start by just saying that this gives you a map at the tracial level. Okay, so you get a map from traces B lower infinity to traces on A. This one's contravariant the way I've written it. To start. Now, remember I said JB is tracially null stuff. So when you mod out by it, you didn't really lose, it's tracially null, so you don't lose traces, I guess. You can think of it that way. So really you end up with a map from traces B up or infinity traces on A. I mean, they really have the same traces. Okay, now I mentioned B upper infinity has a rich von Neumann algebra-like structure. Okay, and here the idea is to glue together classification, which is already available to us, classification of maps from A into finite von Neumann algebras. Okay, which is, I mean, into finite, this is really a consequence of Kohn. And this gluing procedure is really something that was done in some nice work. You can read about it. It's already in the archive. This is Jorge Castillejos, Sam Evington, Aaron, and Stewart. So this gluing framework, I mean, which had appeared before, but I guess you can find it formalized in a paper by these 4 gentlemen, and also relying on some work with the same guys in Wilhelm. So you can glue together this kind of classification that you get just from this von Neumann algebra structure and get a map from A to be lower infinity. Okay, you can classify maps like this. So with a suitable uniqueness statement as well, you get a map here already. Okay. And I won't get too much more technical, so I'll finish probably in about a minute. But the idea now is you have a star homomorphism here that you want to lift. What you have is this star homomorphism, and you also have something else because you have a map at the level of K theory, which gets you KK elements, so a generalized star homomorphism. And you have this map here, which you want to lift in kind of a coherent way along with this KK element. Okay, and this is where, this is where the fun, I think, well, not that this isn't fun, but this is where the fun in our approach that we're responsible for lies, which I believe Chris is addressing some of this, but I don't want to, I mean, he can tell you what he's going to talk about, but I think he's going to be addressing some of this. This is what we refer to as our classification of lifts. And what is the idea here? Basically, you're going to be using extension theory, okay? And this approach, which had appeared earlier already in some work of Chris, these ideas to show one can lift theta. And I'll just draw a picture up here. Basically, you consider a related extension, a pullback extension here. Okay. And as I mentioned very briefly, extensions of C-star algebras can be related to KK theory. You have this KK element, you have this theta, so there's enough ingredients, JB is sufficiently nice that you can actually split this extension. Okay, using your KK-based machinery and find this lift. Okay. The last thing that's left to do is not straightforward at all, but might seem a bit like an afterthought the way I'm writing it. It's really just the packaging that I mentioned. You have to package it neatly in terms of the total invariant. Okay, all of these classification results, you won't see the total invariant appear essentially at all. And then it is really something that you want to do. Okay, something that you need to do. Okay, I think I'll end my talk there. Thank you.